Alright, in this lab we are going to look at faithfulness, especially when it comes to evaluating the output of an LLM answer within a retrieval augmented generation pipeline. Now, if you've been following LLM Chronicles, you see or you remember that the last episode was about all different metrics that we can use to evaluate hallucinations in our retrieval augmented pipeline. Not just hallucinations, but in general, metrics to check the quality of the different aspects of the pipeline. For this particular episode, we will focus only on faithfulness down here, because this is the most useful and immediately applicable metric that you can implement in production if you have a retrieval augmented generation pipeline. And this is what I find the majority of my clients are doing when they are deploying in production. You don't really need to do anything. It's just an additional check, an additional call that you can slot in at the end, and it simply reduces the chance that you are going to display an answer with incorrect or hallucinated information back to the user. Now, we are not going to talk about the other metrics in the Ragas framework like context relevance and answer relevance. Refer to the previous episode or look at the Ragas documentation. But my comment here is that a lot of these metrics are not as accurate at measuring what they claim they're measuring. This is what my clients find when they actually run their own tests. And most importantly, the other metrics that are not faithfulness tend to be more useful when you are developing your RAG pipeline. So you create a data set and you test it offline, or better, you don't test it in production. You just test the quality of the pipeline, and maybe you can go in, change the embedding models, the chunking strategy, change the LLM and see if things improve. But when you have a system, you've deployed it in production and you want a real-time check, faithfulness is what you're looking for. So here we'll look at different ways of implementing these checks. All of these are LLM judges or LLM verifiers. And we'll look at how Llama-index does this. We'll look at Ragas, and we'll also look at Azure groundedness checks. This is an API that Azure offers you, essentially an LLM-as-a-judge that you can use to check whether an answer is grounded in the context. Now here I have already started by running all of the installs and the imports. We are going to use a judge LLM, so we need an LLM, and for this one I'm using OpenAI. You could change it with any other good LLM. And just as a reminder, very quickly, what a retrieval augmented pipeline gives us that we can use to evaluate is the question the user asked, the context that we retrieved from a database. Typically, this is a vector store where we've taken our documentation, divided it into chunks, embedded it, and then we retrieve this context by doing a semantic search or a similarity check between the question and the different chunks. We retrieve the top chunks that we think are relevant to answer the question, and we give them to the LLM, which then produces an answer, hopefully based on the information in those chunks. So here with faithfulness, what we want to check is whether the answer the LLM produced is actually grounded in the context that we retrieved, or if the LLM misinterpreted it or added information that should not be there. Now, here I have a sample or two samples, which basically give us the three elements that we typically need to answer, to evaluate faithfulness. So we need the question the user asked, the LLM answer, and the context we gave to the LLM. Here, the context really works as the ground truth. We want that answer to only contain information that can be inferred or that's directly stated in the context. Now, my two examples, let me copy them out here so that you can see them better. So the question the user asked is, when was the first Super Bowl? The answer, the context provided to the LLM is this. Imagine it comes from a Wikipedia page that was embedded and put in the vector database, and the LLM provides the correct answer, giving the same date that we've got in the context. And then here is a hallucination where the LLM answers with the incorrect date. So this is quite an obvious hallucination. So we have these two samples, and now we're going to check, first of all, with an LLM-as-a-judge using gpt4o-mini. And just to remind you, this essentially means after we have collected all of the information, that we simply write a prompt to the LLM asking it to analyze the context, the question and the answer, and to give us a score as to whether that particular answer is in line with the context. And sometimes we also ask the LLM to provide the reasoning behind this. And that's exactly what I have here. I'm using LangChain because we spoke about it in the previous lab when we did the LLM agents. I think the new interface that they have is quite simple and nice to use. So I'm sticking to that, but it should be fairly easy to switch it to anything else. Now, the prompt here is the key. It's basically the same version of this prompt, just extended. And let me copy this out so we can take a look. So given the following question, document, and answer, again, there's three variables here that we get from a RAG pipeline. You must analyze the provided answer and determine whether it is faithful to the contents of the document. The answer must not offer new information beyond the context provided in the document. The answer must not contradict information provided in the document. Output your final verdict strictly following this format. Pass if the answer is faithful to the document, fail if the answer is not faithful, and then it goes on providing those answers and telling the LLM how we want the output. In this case, it's a JSON object with score and reasoning. Now, you could change this, by the way, depending on the LLM, you could have a totally different prompt. For example, you could ask it to provide a score between 0 and 1. You don't have to ask it to provide reasoning. And we'll actually see examples of different prompts you can use. This particular one, I have actually taken from the Lynx paper. Let me just bring it on the screen. If you remember from the last episode, the people that created the Lynx LLM had essentially fine-tuned Llama 3 on this particular prompt. Again, this is exactly the prompt I'm using, but it turns out it works well with GPT4o as well. So there it is, and here I am using gpt4o-mini. gpt4o-mini is quite a good LLM. It's pretty fast, it's cheap. You can experiment with obviously other LLMs. One important thing to mention here is that we set the temperature to 0. This is quite normal when we're dealing with LLM judges, or we want to use an LLM as a verifier. We actually don't want it to be very creative. Now I'm simply taking the prompt that we had before, declaring the variables, and then wrapping it into a simple chain. So this is the prompt, that's the LLM we instantiated, and that's the string output. And now we can pass the sample, for example, containing the hallucination. And as you can see, if we look at the output, we have score fail, as we are expecting, and the reasoning tells us why it thinks that, because the answer incorrectly states that the first Super Bowl was held on January 15, 1989. So in this particular case, obviously it's such a simple example, and just to double check, if we change it to the correct answer, the score should be pass, because obviously it does not contain an hallucination. Now, when I look at this chain, because the output is JSON, I just want to modify this chain to parse that output so it's easier later on to work with. So I'm just switching the string output parser to the JSON output parser. So instead of handling or manipulating this as a string, I can actually access the individual fields in that particular output. So that's how you use an LLM as a judge to detect whether there is an hallucination. You could try to do the same again with the Lynx LLM. Remember, this is the one that comes from this paper over here. It's a pretty good paper, and they also have a data set that we're going to use later. I have here the code. If you want to run it, you are going to need a GPU, and this is an 8 billion parameter LLM, so you're probably going to need an A100, and it's going to take maybe 30 minutes to 1 hour to download and load this model in memory, so I am not going to use this. But feel free to experiment if you have access to those GPUs. But you can see that the prompt will stay exactly the same. Now let's take a look at how Llama-index does this. Llama-index is a general purpose framework that you can use to build retrieval augmented generation pipelines and LLM applications. And they recently introduced in the framework, let me see if I have a better link. They recently introduced some metrics similar to the ones that Ragas has. You can see them here, to evaluate aspects of the retrieval augmented generation pipeline. And obviously here we are interested in the faithfulness evaluator. It's really simple to use. From Llama-index, we import the faithfulness evaluator. Here again, I'm using gpt4o-mini. Feel free to change it, for example, with gpt4o and see how this changes. So I instantiate the evaluator with the judge LLM that I want to use, and then we run the particular sample. So, one thing which is important to mention here is that this does not require the query. It doesn't use the user's question, whereas the prompt that we had before also provided a question. The Llama-index one does not require the question. It only wants the response and the context, and then it gets you this evaluation result object. And the most important part here is whether or not it has passed the check. In this case, it hasn't passed it because obviously we know it's false. It's got an hallucination. But if I rerun this with the sample that doesn't have the hallucination, now passing equals true. So it's pretty simple to work with. And if you go and take a look at the source code from Llama-index, you can see that this is implemented very similar to what we did before. They have an evaluation prompt template, and then they prompt whatever LLM you're passing with this particular template. So please tell if a given piece of information is supported by the context. You need to answer either yes or no. So obviously here, the format of the answer that they're telling the LLM to use is a little bit different. They give it some examples, so they do a little bit of in-context learning, whereas in the previous one that we used, there was no in-context learning, so it was zero shot. And then obviously we've got the query string, which is the user question, the context, and then obviously the LLM completes the answer with yes or no. And if you look at the code, that's basically what that faithfulness evaluator is doing. And one thing to mention is that they have also different templates for different LLMs. They will have tried these, for example, with Llama 3 8 billion, and they found that these prompt works better. You can see that the examples or the in-context learning, multi-shot kind of learning is more detailed than what they have before. And again, that's an advantage of using a framework that they will have experimented with different LLMs. Okay, let's now take a look at Ragas. Obviously, Ragas is one of the most widespread frameworks when it comes to evaluating retrieval augmented generation pipelines. They have a lot of metrics, and this is how they implement their faithfulness metric. This is still using an LLM as a judge, but if you remember, there are two steps here. In the first step, they give the LLM the answer and they ask it to break it down into simpler factual statements. So the LLM, in the first call will produce the list of statements, and then they give the context to the LLM and they ask it to determine whether the context provided matches the facts in the statement. And this idea is obviously to try and do something a little bit more sophisticated. If we go and take a look at these, we can see obviously the documentation. Now, more specifically, I want you to focus on how they calculate the score. So the score is the number of claims in the generated answer that can be inferred from the context divided by the total number of claims. So the way that this would work, let's say there are 3 claims that the first LLM call extracted, then they ask the LLM again which of these claims can actually be substantiated by the context, and then they calculate the score that way. Now, the first thing to see here is that obviously here we've got multiple LLM calls. So this is more expensive, will take more time to process, which is something that you have to consider. And in practice, I should say, again, when my clients go and check these on their own pipelines, most of them find out that they don't really get much benefit from these in the domains that they're testing these in. So although this is more complex and in theory makes more sense, in practice, I should say not many of the clients I've seen in the industry are actually using these, at least as a real-time check. And also Ragas is very interesting, but I'm not sure the code base is what I would call production ready. There is a lot of changes and naturally quite a lot of bugs. I mean, it's an open source project coming from a research paper. So I'm not saying Ragas is bad. I'm saying I'd be conscious of just blindly deploying these in production. It is again more useful if you want to evaluate your pipeline at development time. Anyway, how would you use this? So obviously we do all the imports and we need an LLM evaluator or an LLM judge, gpt4o-mini, and then we also need an embedding model. Now, to be honest, we don't need this embedding model here, but there are some other checks that Ragas does that actually, for example, answer relevance, which actually require the embedding model. But again, we don't need it for the faithfulness, so you can disregard that. Then we get the faithfulness metric and we run it on our sample. So we use this single turn score and we pass the sample in this format. This single score comes from the Ragas library. And so the score for these should be 1, because obviously there is no hallucination. And if we change these to the example with the hallucination, the score should be hopefully 0, which we get correctly. Now, again, what I want to do is to show you a little bit of the source code of these, which we can find in a Git repository. It's fairly long because actually Ragas has got a lot of other things in these checks, but you will see at some point, for example, you have a prompt. Your task is to judge the faithfulness of a series of statements based on the given context, which is likely the prompt that they're using for step number 2. And then there will be another prompt for step number 1, where they're asking the judge LLM to break down the answer. It might be somewhere in here where they are breaking out the text using this sentence segmenter, I guess. I'm going to spend too much time looking for these. I mean, you can take a look at it yourself, but this is likely from a first glance what they're using with an LLM behind it to split the answer into different statements. Now, there is another way that Ragas implements faithfulness. This is instead of using an LLM at the second step, they use a classifier based on T5, which is a model that Google created. And obviously this is a much smaller model, and it is a classifier, so it's not generative. And the idea is the inference will be faster. Now, problem is here that I haven't been able to get this to work, meaning that this runs, and in this case returns 0. By the way, this is how you instantiate it, faithfulness with HHEM. But as I said, if I give it a sample that does not contain hallucinations, obviously the score should be 1, but when I use these, the score I get is still 0. And I don't think that I am doing anything particularly wrong. This is probably some issue with this particular version of Ragas, which I think is 0.2 point something. And maybe this is, again, a chance to tell you that Ragas is a very nice project. The paper is very good. But when it comes to doing things in production, I wouldn't use Ragas yet. I don't think it is to a maturity state that would make me feel comfortable. Almost every time I use it, there are little bugs and issues. For example, the first part of this pipeline, sometimes it will return no statements, even if there is a valid answer. So you might see a warning when you're processing stuff where it tells you that, again, it can't find statements. And I don't know why that particular part is failing. It doesn't seem to be due to the LLM. It's probably some issue that they will resolve. But again, that's why I wouldn't use this as a real-time check in production. I might use it as I am developing something to check the quality of a pipeline. And most of my clients that have tried it do agree, and they use the other methods that I showed you. Also, you should consider that this one requires 2 LLM calls to be done one after the other. And so it will add latency and it's more expensive. So again, probably not yet the best check to have in production. And in spite of the complexity, I think a lot of the evidence, empirical evidence, again with my clients, is that this faithfulness check doesn't necessarily perform better than a simple gpt4o-mini LLM-as-judge. And there are things like Lynx, which often perform even better. So that was Ragas. Again, I'm not saying that Ragas is not good. I'm saying it's probably not production yet. It's very experimental. Finally, I wanted to talk about Azure groundedness checks. Now, this is an API which is part of the Azure AI Content Safety services that you can use to check whether an answer is hallucinated or not. So it works very similar to what we saw before. In order to be able to use this, obviously you need an Azure subscription and you need to create a content safety resource, which is going to get a specific endpoint or URL for you to use. And it's also going to get an API key. So once you've got this, you can essentially directly call this endpoint with your key and providing this JSON payload to the endpoint. You can see that this is in preview, as it says. There is not even or currently there is not even an SDK that you can use, but it's fairly simple. And as you can see, it takes the query, so the question, it takes the grounding sources, so the context as we've seen, and then the text, which is the LLM answer, and it tells you whether this is an hallucination or not, in its opinion. Now, one thing that I find interesting here is that you have to specify a domain, whether this is a generic question or I think right now they only support medical. I'm sure that they will add financial or similar things, and then the task, whether this is a Q&A task or a summarization task. So clearly they've seen that there is a difference and they're trying to adapt around that. Now, looking at this and at the output, I think this is still a judge LLM. So it will be something like this. Now, they might be using GPT-4 or they might be using a specific model that they have fine-tuned. Obviously, we don't know this. But I have wrapped this function, this API, into this AZ check function. As you can see, I've simply mapped that Python code there. And an additional thing to be mindful of is that you can also ask it to provide you the reasoning behind its decision. Again, this is identical to this, where you ask the LLM not just to make a decision, but to also provide the reasoning. This is why I think this is a judge LLM. Now, let's run this and run it through a sample which contains an hallucination. And indeed, the result is true. Now, be mindful here, because everything we've been doing so far has been asking the question whether or not that answer is faithful to the context. So you get true if there is no hallucination. Here, instead, the way that they are asking the question is whether this answer contains an hallucination. So it's true if this is an hallucination. I honestly think they chose very weird wording. This ungrounded detected, basically meaning I have detected that this answer is ungrounded. It's a bit jarring. I wish they just called this faithfulness true or faithful, true or false. But anyway, obviously, if we try like this with no hallucination, we are going to get ungrounded equals false, as we are expecting. All right, to close this episode, I wanted to show you HaluBench, which is a benchmark put together by Patronus AI. So obviously the same folks behind the Lynx LLM. And it's basically a dataset that you can use to evaluate hallucinations, or to evaluate your hallucination detection system. I really like this because they have put together samples from all sorts of different data sets, such as RAG Truth, which is a pretty general purpose RAG hallucination dataset, but also Finance Bench, PubMed Q&A. So they have also domain specific knowledge, making this dataset a little bit more interesting when it comes to the type of evaluation that you can do. So this is all open source. We can proceed to download this from Hugging Face, and There are around 15,000 samples in here, and we can take a look at one of the samples. It's actually pretty easy. There is obviously a question, a passage, which is the context that the LLM was given to answer the question, and then there is the answer of the LLM, so the usual triad that we've been seeing so far. And then most crucially, you have a label. If this is set to pass, it means that the annotation, the manual annotator determined that this is not an hallucination, and if it's failed, it means that this is an hallucination. So obviously we need the label when we are evaluating our controls, so we can check whether the prediction is correct or not. Now, because the dataset is quite big, we are going to make a smaller version of this dataset that we can use to evaluate the checks that we've been discussing. And I'm going to do that by sampling 50 random non-hallucinated samples and 50 random hallucinated samples. So I have 100 of these. And then I am going to create a function which I've called check hallucination, which takes the usual triad that we need, plus an evaluator name. The evaluator name being one of these four: LLM-judge, gpt4o-mini that we did at the very beginning, Llama-index faithfulness check, the Ragas faithfulness check, and the Azure groundedness. And obviously it implements the same code that we saw before. So we got this, and we can test it out. Easy way to do this is to have all of these in an array, and then to iterate through that list calling check hallucination on a sample that we know. Again, here I'm not evaluating, I'm just checking whether there is any error in here that would make it fail. But we can see that this works fine. So now we can run all of these on the mini dataset that we created. And again, you can read the code yourself, but here I have an evaluation function which takes the dataset, the evaluator name, iterates through each sample in the dataset, calls check hallucination with that evaluator name and the particular sample, and then stores whether or not this answer is correct. So later on, obviously, we can compute accuracy and compare things. And now this here is simply going through all of the evaluators, calling evaluate, collecting the results for analysis. Now you can see that obviously it starts with gpt4o-mini. There are 100 samples, so it's going through each and every of these at the same time. If we wanted, we could parallelize these. Obviously, this is just a toy example. It is still going to take some time to go through 100 examples, 4 or 5 times? How many have I got here? 1, 2, 3, 4. So there are essentially 400 calls that this needs to make. So I'll come back when this is done. All right, the evaluation is finished, so we can go and take a look at the results. Now, the first thing I want to draw your attention to is the time this took. So the LLM-judge gpt4o-mini took around 3 minutes to go through these 100 samples, whereas the Llama-index faithfulness, still using gpt4o-mini, took only 36 seconds. So wait a second, why such a difference? Aren't they doing the same thing? Well, the difference is, if you remember, that the gpt4o-mini that we prompted directly, our prompt is, first of all, bigger because it also provides the initial question that instead is not provided here in Llama-index. Llama-index only provides the context, and the other major difference, what's really making a difference, is that here we're asking the LLM to produce reasoning. We don't just want the score, pass or fail. So obviously the reasoning is much larger and requires multiple tokens to be generated, whereas here we are simply asking for yes or no. And this is what makes the difference here. You will also notice that the one that took the longest is obviously the Ragas faithfulness checks. This is due to how many multiple calls need to be made. This basically took twice as long as the standard single call GPT4o-mini with reasoning. And finally, Azure took around 3 minutes as well. So roughly what we were expecting. Now, if we put all of these results together, we can see how well the different methods did on this mini dataset. So the best of all was GPT4o-mini with 84% accuracy, followed by Llama-index, and then followed by Ragas, which had only 63% accuracy, and then Azure, which had 70% accuracy. Now, again, a takeaway point from here is that the fact that Ragas was the slowest, the most complex, doesn't necessarily mean that it's the one that's going to get the best performance. And whenever you're using a good base LLM, you are going to get pretty good performance anyway. Now, obviously, this is a small data set. You would need to rerun these tests on the larger data set to get a better idea, because we just sampled 100 random rows from there. And typically, what I recommend and what my clients do is to take real inputs and real outputs that they collect from their RAG pipelines as they're used, getting humans to annotate them, and then use that as a benchmark, because that tells you the specific control, how it does in your context. So that's all I had for this video. Thank you very much for sticking until the end of the video. It really makes a difference for YouTube. And again, remember, if you can, to play the YouTube game, which basically means to like the video, drop a comment, subscribe if you're not subscribed. It really helps a small channel like this one to grow and to be recommended to more and more people. YouTube can be, or the YouTube algorithm can be pretty harsh with technical content like this one. So if you want to support the channel, you know what to do. See you next time.